Okay, so it's a pleasure to have Evan giving a presentation today. He is a new postdoc in our group, started just about a month ago, fresh from Stony Brook, finishing his PhD with Dimitri Kharzaev. And today, I think he will be telling us more about his PhD research. And then during his postdoc in the quantum computing group, I guess he will be focusing more on the quantum computing side of things. So with that, please, Evan, start.
Yeah, hello everyone. The title of my talk is Chiral Fermions for Quantum Computing. I have to give you a warning in the beginning itself that the quantum computing side is mostly still underway. Some of it is kind of speculative, but I will talk about one piece of the work I did in my PhD, which we think is a step in the direction. So this would be the outline of my talk. I will give you an introduction of all the basics because I think this is a broad audience, and while materials are not common knowledge, so I will go over the basics. Then I'll talk about chiral magnetic photocurrent, which is one of the things that I did in my PhD, which potentially is a step in the direction of applications in quantum computing. And I will also talk about the chiral qubit and transducers, where this chiral magnetic photocurrent comes into play. But both of those applications are still in the very nascent stage. So I just wanted to give a disclaimer in the beginning itself. And please do let me know if something is not clear. I was trained as a nuclear physicist, then I started doing condensed matter physics. So often I assume some things are known to everybody, but maybe not. So please stop me if something is not obvious. So first, we will start with what chiral fermions are. So most of you would know all of these things, but just bear with me. So fermions, we all know, are particles which obey Pauli exclusion principle. That's one way in which they differ from other particles, say like bosons. And we also know that fermions, relativistic fermions very specifically, are represented by the Dirac equation. And the Dirac equation is a 4-component equation. So you can see it's a differential equation, but it has 4 components. This is in a particular representation of the Dirac equation called the chiral representation. If you look at the right-hand side, you can see that it's very suggestive of Einstein's relativistic energy momentum relation. There is this momentum term here, and there is an mc square term sitting here. It looks like the square root of this somewhat. And it has 4 components. This is what is important for us. Now, the 4 components in the Dirac equation are usually coupled. I have named the first 2 components as F and the second 2 components as G just for convenience here. And the structure of the Dirac equation is roughly like this. So if you just expand this matrix equation, you will see that the differential equation for F depends on G. So say you start with F at 0, but G is at a finite value. F will start increasing according to this differential equation. So F depends on G, and you cannot just talk about F and G separately in this kind of equation. However, if the M here, which is mass in the Dirac equation, is set to 0, then F and G decouple. So F is dependent only on F at that point. So then if F starts at 0, it stays at 0, and G just does its own thing. This is exactly what happens to the Dirac equation if mass goes to 0. It decouples into two equations. These equations are known as Weyl equations, and these particles are known as Weyl fermions. So there is another name which is used for these particles, chiral particles. Chirality just comes from the Greek word for hand. So there is a sort of handedness to these particles. They differ in the following way. If you point your thumb in the direction of its momentum and wrap your hand around in the direction of their spin, depending on whether you have to use your left or right hand, you can distinguish these two types of particles. So they are called chiral particles, and they are often referred to as right and left-handed particles because of this. I will be using the name Weyl and chiral interchangeably. So Weyl fermions were proposed about 2 years after Dirac proposed his equation in 1929. Soon after, they were thought to be very good candidates to describe high energy physics or particle physics, things like neutrinos. But around late 1950s, it was found that neutrinos needed to have mass. So neutrinos were no longer thought to be Weyl fermions after that. And in nuclear collisions, if the energy is high enough, the light quarks, U and D quark, can be treated as Weyl fermions because the mass becomes irrelevant. So even though neutrinos turned out not to be Weyl fermions, they are still used in high energy physics in the context of nuclear collisions. But they also developed in a slightly different direction. In 1930s itself, it was recognized by Cornelius Herring that these particles could emerge in condensed matter context. But it took about 85 years to observe Weyl fermions in the laboratory. I think it was seen for the first time in sodium bismuthite. So how do Weyl fermions arise in condensed matter systems? Again, we all know about block states, and these kinds of energy level diagrams are we learned about them in high school or college. So we all know this cartoon where we distinguish between insulators and metals. Oh, sorry, I didn't mean to do that. We can distinguish between insulators and metals depending on where the Fermi level lies and how many of the states are occupied. So if the states are occupied to this level, you can easily have excitations because they don't require any energy. These are metals. Here there's a gap, so they are insulators. We have a third category of things called semimetals. As expected from the name, they are just things with a very, very small overlap. And the other thing to notice from this diagram is the effective mass of these block states is nothing but the curvature of this energy momentum diagram. So what would it look like if a particle had zero mass, if a block state had zero mass? Basically, it would have to be a straight line. So that's what we are looking for. And this straight line would have to be near the Fermi level, because if you have that kind of a straight line or a cone rather, maybe straight line is not the best description. It should be like a wedge, like a cone, something like this. And it has to be near the Fermi level, like I said, because if it's not near the Fermi level, if it's somewhere deep inside the Fermi surface, you cannot access it, so it's not very useful. So this is how massless or Weyl particles can arise in condensed matter context. And it turns out that there are some materials whose band structure looks like this. I've given an example here. I think this is tantalum arsenide. And they have this kind of conical touching points. You might be familiar with these conical touching points in the context of graphene. Graphene's Dirac points are very famous, but the thing is, we want these particles to exist in 3 dimensions because certain effects we are talking about will only exist in odd dimensions. So these are special because they are 3-dimensional particles with these kinds of conical touching points. Again, do stop me if something is not clear. It's a little strange to talk to a screen. So I would appreciate you stopping me if something is not clear. Okay. So there are many particles, there are many materials known right now which have these kinds of conical touching points. I have put a picture of tantalum phosphide here. So the crystal structure is given here, and this is just showing the symmetries. But the important thing for us here is to understand this picture. So as you can see in this picture, they have plotted energy and momentum. So this is just the part of the Brillouin zone that they are showing. The part where this conical, I'm sorry, something is making my slides skip accidentally. I think it's just me moving the mouse around, so I'll be more careful.
Can I ask a question?
These conical touching points. Sure, please.
Do you want the conical touching points to be at 0 momentum, or are you not caring about where it is in the Brillouin zone?
No, we don't care where it is in the Brillouin zone. It doesn't have to be at 0 momentum. But you are touching on a very important point there. In high energy physics, Weyl particles will always be touching at 0 momentum. Free particles cannot have Weyl points at non-zero places. But in condensed matter systems, you can have these touchings at non-zero momenta. In fact, when they are at 0 momentum, they tend to be very special. Some symmetries usually are involved in those cases. And in general, they are not at 0 momentum. And again, thanks for the question. In condensed matter systems, we can have this very special case of the 2 types of Weyl cones not even being at the same point. They can be separated in momentum. So this is actually an illustration of such a material where your left-handed cone and your right-handed cone is separated in the kx direction, but they are overlapping in the ky and kz direction. So you can even have situations like that. If they are separated in momentum space, they are called Weyl semimetals. If they are not separated in momentum space, they are called Dirac semimetals. So that's the distinguishing feature between Dirac and Weyl materials. So these are just various diagrams showing the same thing. This is the cross section of this diagram. It's also good to spend a minute trying to understand what this is. So this is showing 3 momentum directions, and energy is shown as a color in this picture. We will come back to this picture later, so please stop me if something is not clear at this stage. And they can also see this in experiments. I don't know the details of these things, but this is some ARPES measurement of the cone. So you can see this in real experiments, what these cones look like and things like that. So I will come back to applications in quantum computing later, but just to give you a start. We do quantum computing with various kinds of information carriers, charge, superconducting current, spin. So it's kind of natural to ask, can we do quantum computing with chiral fermions? And then we have to also answer the question, well, why would we want to do quantum computing with chiral fermions? We will come back to that later. There is also another application of chiral fermions, which is in transduction. It will become obvious why these are ideal candidates to make transducers, but that's also something to keep in mind. So a transducer, I didn't know what a transducer was. Probably you all do, but I'll just mention a transducer is something which converts energy from one form to the other. And in this particular context, we are referring to things which convert energy from one frequency of the electromagnetic spectrum to another frequency of the electromagnetic spectrum. These have some special properties which make them very suitable for that. That's kind of the end of the basic introduction. Now I will step into chiral magnetic photocurrent. If there were any questions about the basics, please, this would be a good point to ask. Okay, so I'll go ahead. Today I will be talking mostly about chiral magnetic photocurrent. So what is chiral magnetic photocurrent? This is the phenomena. You take a Dirac or a Weyl semimetal, which is basically a condensed matter system which sustains Weyl fermions. If they are at the same point, it's Dirac. If they are separated in the momentum space, they are called Weyl. If you just take such a material and put it in an external steady magnetic field and shine circularly polarized light onto this material, you will see a current in the direction of the static magnetic field. This is pretty interesting in itself, because you get current proportional to the magnetic field in the direction of the magnetic field. This is not allowed by Maxwell's theory, typically. So it's a very interesting phenomena, and these are while physics plays a very essential role in this effect. This has only been theoretically predicted, but Brookhaven and Stony Brook University has quite a bit of experimental capabilities related to Dirac and Weyl materials. It has been delayed a little bit because of Corona, but we are hoping that we can actually see this in experiments sometime soon. So this is the phenomena. Now I'll go into the physics of it. So the first ingredient in order to describe this is something called chiral anomaly. I will not go into the details of this, but this is what you need to know about it. In classical mechanics, we all know Noether's theorem. It's a very powerful theorem which states that associated with every continuous symmetry, there is a conserved current. So the theory of Weyl semimetals, the theory of Weyl fermions, or just Maxwell's equations with matter put into it, they have something called the chiral symmetry. Essentially, the left-handed particles and right-handed particles, it's the symmetry which converts between these two things. They have chiral symmetry. So classical mechanics tells us that chiral charge, I'll define what chiral charge is in a second, will be conserved because of this chiral symmetry. And it's implied by Noether's theorem from classical mechanics. What is chiral charge? I have left-handed particles and I have right-handed particles, right? And these left-handed particles and right-handed particles have electric charge. They are pretty much like electrons, except for the fact that they don't have mass. So they have electric charge, but you can also define something else, which is the difference between left and right-handed particles. So this is the definition of chiral charge density. If I add the left and right-handed particles, you will just get normal charge. So this is kind of like the imbalance of left and right-handedness. That's what chiral charge is. Classically, chiral charge should be conserved. But when you go to second quantized formalism, there is an anomaly. We call it an anomaly because it's a classically conserved quantity which is not conserved in quantum mechanics. This anomaly says that chiral charge will not be conserved. So this is a purely quantum mechanical effect, and while physics is essential for this effect to happen, we'll just take this effect as is. And the expression for the non-conservation of chiral charge is the following. The rate of change of chiral charge will be equal to E dot B, where E is an electric field and B is a magnetic field. So if there's no electric and magnetic field, chiral charge is conserved. But if there is an electric and magnetic field and there is a component of the electric field parallel to the magnetic field, then it will be violated. Chiral charge conservation will be violated according to this equation. It comes because of this diagram, and we can talk about the details if somebody is interested. In a real material, in particle physics, again, it's just this first part of the equation. But in real materials, there can be scatterings from which are chiral charge non-conserving scatterings. So there is going to be a small dissipation term added to this equation. We will be ignoring this dissipation term for the rest of the discussion, but I don't want to give you the false idea. So yes, there is some dissipation in real materials, but for the most part, chiral charge is the non-conservation of chiral charge is given by this equation. So what does this equation mean? Again, skipping slides, sorry. What does this equation mean? If you just take a material and you just start with it and you look at the chiral charges in that material, you will have the same number of left-handed particles and right-handed particles. What would the Fermi sphere look like in that case? They look like to be of roughly the same size. As I have shown, not roughly, they should be of exactly the same size if there are equal number of left and right-handed particles. Now, I subject it to E dot B externally or somehow. Then this non-conservation of chiral charge essentially will induce an imbalance between the left and right-handed particles, right? So one of them will get smaller and the other one will get bigger. So in terms of the Fermi sphere, the anomaly does this. It's easier to think in terms of these pictures. That's why I'm moving away from the equation into these things. But do stop me if this is not something is not clear. So this is what anomaly does in terms of Fermi sphere. The next ingredient I need in order to talk about chiral magnetic photocurrent is the concept of helicity of light. So we know that light can be circularly polarized. So left circularly polarized light and right circularly polarized light definitely is chiral. They have a handedness to them. We want to quantify the chirality of left circularly polarized light and right circularly polarized light. We choose to quantify that in this very specific way using something called the Chern-Simons current. So you can see this A is the 4 potential and F mu nu is just the A is the vector potential and F mu nu is the electromagnetic field tensor. We have to write it in this particular way, and this H, if you calculate it for left and right, you will see that it's of opposite signs. This is a good way to characterize the chirality of light. But there is something strange about this helicity. You will see that the vector potential comes into it directly. Usually when you characterize a physical quantity, you are not supposed to have vector potential coming into it directly, right? Because it will depend on the gauge. Yes, H is a gauge dependent quantity. But the reason why we have to use a gauge dependent quantity in order to characterize the helicity of light for this discussion is because this effect is related to anomaly. So anomaly comes into picture here through this vector potential in the helicity. But in all our physical equations, we do not use helicity directly. We use the derivative of the helicity. So the derivative of helicity does not have is not gauge dependent. So we characterize the helicity of light through this apparently strange looking quantity. It's gauge dependent, but it's okay because we will only use the derivative of the quantity which is not gauge dependent. Why did we bother to use such a clumsy way to define the helicity of light? It turns out the helicity of light plus chirality of the charges in the material, this quantity is conserved. This was our key insight. If you add the helicity of light and the chirality of the charged particles, you get a conserved quantity. And this, since it's a conservation equation, is very robust and very powerful. It doesn't matter which direction the light is coming. It doesn't matter how light is dissipating in the material. None of those things matter. The total helicity the total quantity is conserved. Now we can think, okay, let me just explain one more thing on that slide. We can think about this. Light is coming from outside. It has a finite helicity depending on if it's left or right. Light will enter the material and light is going to get absorbed by the material. Once light is absorbed by the material, there is no helicity for light, right? So where did the helicity go? We have a conserved equation. So helicity of light has to necessarily turn into the chirality of fermions once the light is absorbed. This is essentially what is happening in this system. I shine light to the material, the light gets absorbed. Once the light gets absorbed, this conservation equation dictates that it has to go into chirality of the fermions. So this will only happen if the light is getting dissipated in the material. Dissipation is working to our advantage in this situation. So if you have a transparent Dirac or Weyl material, light will just go through it. But most Dirac and Weyl materials absorb light very heavily. So the chirality will get transferred to the fermions. There is a more physical way to see this. Okay, I'll just stop for a minute for questions. Is everybody with me so far? Okay.
I mean, you're just
So
effectively
electric
writing. Sorry. You're effectively just
Sorry?
writing. You're effectively just writing the usual FF dual term in the axial anomaly as a total divergence and saying.
Absolutely. That's
Yeah.
all that this is. I took the axial anomaly term and took it to the left-hand side. Instead of saying that this is equal to that, I just took it to the left-hand side. That's it. That is the key insight in this. But there's a physical manifestation for that, which is if I shine circularly polarized light, I'll get chiral charge in the material. So you're absolutely right. That's all that this is. Yeah. So physically, what is happening? All this is good, but I am in a condensed matter system, and I know that anomaly is all good, but you have a Dirac sea and everything, so something must be happening here. If light enters a dissipative material, this does not have to be a Weyl material or anything, any dissipative material like a metal. It turns out that there will be a phase lag between electric field and magnetic field. Just elementary electrodynamics. So if there's a phase lag between the electric field and magnetic field, E dot B will no longer be zero. In vacuum, E dot B is always zero for light because electric field and magnetic field is perpendicular. But in any dissipative material, it is non-zero. So what is happening is light enters this Dirac or Weyl material, and because of dissipation, E dot B becomes finite. And the anomaly equation is causing this E dot B to lead to the generation of chiral charge. This is just another way of looking at it, but even without this, it might be obvious to you if you are already familiar with anomaly. This is all well and good. I got chiral charge, but you cannot observe chiral charge directly. Well, it's not easy to observe chiral charge directly. But in the beginning, I said that we get an electric current. Where do I get the electric current from? That's what I am coming to next. In order to understand that, we need to know what the Landau levels of these chiral charges look like. So we all know what the Landau levels of massive electrons look like. They are parabolic and they have equal distance between them. Chiral charges have this, chiral fermions have these interesting looking Landau levels. Again, I am sorry, the slides are skipping. Okay. Yes. chiral charges have these interesting looking Landau levels. The left-handed chiral fermions and the right-handed chiral fermions have different spectra. As you can see, there is a Landau level that passes through 0, first key observation. Secondly, there's only one velocity in this case and the opposite velocity in that case for the 0th Landau level. The higher Landau levels are the same. Again, there's a physical way to understand this. In the magnetic field, the spin aligns with the magnetic field, and you can think about it that way, but the Landau levels look like this. Now, let's go back to our Fermi sphere picture. What do the Fermi spheres look like? You know, Landau levels just end up being cylinders in this space. So if I am looking at my occupation and I draw the Fermi sphere around these cylinders, it looks like this. The characteristic thing about massless particles is that you have this kind of line in the middle, which massive particles don't have. This is the zero energy line. And you can see that it only points in one momentum direction in case of the left, and the opposite momentum direction in case of right-handed particles. This is good. Okay. Now the next step. Let's see what this implies. Higher Landau levels are cylinders. So there are equal number of particles with positive Z momentum and negative Z momentum. But the lowest Landau levels, if you just look at the left-handed particles, they all have negative momentum, and right-handed particles all have positive momentum. But this won't lead to electric current because there are the equal number of left and right-handed particles moving in opposite directions. So the net charge flow is 0 in this case. So it's fine. It doesn't mean that if you take a Dirac or Weyl material and put it in a magnetic field, you will get a current. However, if you put circularly polarized light on a Dirac or Weyl material, we have shown that the size of the Fermi spheres change. So now when the size of the Fermi sphere changes, if you look at the lowest Landau level, this is shorter than this. Now you have more particles going in the positive Z direction, which means you have more charged particles going in one direction than the other. You get a net electric current. Again, this is something that is called the chiral magnetic effect. It was proposed in the context of nuclear physics. This is not our discovery or anything. We just put these two things together. Chiral magnetic effect was proposed in the context of nuclear theory, and it was observed for the first time here in Brookhaven in case of zirconium pentatelluride through the measurement of negative magnetoresistance. So this phenomena of charge flow in the presence of a parallel E and B field is well known. Our effect is different only in the fact that this E dot B is not supplied by an external field, rather by circularly polarized light. That's the main insight in our discussion. So again, coming back, we said that circularly polarized light will lead to chiral charge via anomaly. Chiral charge plus magnetic field will lead to electric current. We calculated the value of this electric current. So the parameters in this I'll explain in a second. So these H bar and E is just standard, and B is the external magnetic field. This sigma ZZ2 is the coefficient that you get from negative magnetoresistance experiments. So we are taking data from this experimental observation here, because that way we can take care of that chirality flipping scatterings I talked about. So you get a clean expression if you just plug in that number here. Alpha is the fine structure constant, I is the intensity of incoming light, and omega is its frequency. So we derived an expression like this for the current that one would observe, and it's a 25 nanoamperes for tantalum arsenide, 50 nanoamperes for zirconium pentatelluride for parameters similar to what people use for experiments involving these Dirac and Weyl materials. So this is the phenomena. If you have any questions, I can take them here, but otherwise I will move on to the applications. Okay. So now, applications. Why was this interesting to us? Honestly, the biggest interest for us was the fact that this is a direct manifestation of chiral anomaly. Normally, the way you see chiral anomaly in a Dirac or Weyl material is by putting it in an external electric and magnetic field. Here, you get a current without any electric field. So that in itself is interesting. And anomaly is an essential ingredient here. Being able to see it in a tabletop experiment is very exciting. There are other proposed experiments to see photocurrents in Dirac and Weyl materials. They don't use anomaly, but our effect is also special in that it will be present in any Dirac or Weyl material. Because nothing I discussed so far, I didn't use any material specific parameters or any of those things. So this effect is reasonably universal. Magnitude will change, but they don't depend on the specifics of the band structure of the material. So it's pretty universal. It's a manifestation of chiral anomaly. But why is this important for quantum computing? So this is a way to generate chiral charge optically. So far, all the means of generating chiral charge involved having to use external electric fields and things like that. But this is a way to you do it optically, and being able to generate chiral charge optically opens up applications for construction of chiral qubits and things like that. So that's one thing. And second thing is, this particular effect depends on the Weyl cones of the fermions. The Weyl cones of the fermions have this feature that there is no gap. Okay, so there is no. I'm really sorry about this technical issue. It keeps happening. I think I am accidentally clicking, but yeah, sorry about that. Weyl fermions do not have a gap in their spectrum. So typically, this expression I showed you here for the current, I can keep using lower and lower frequencies. There's no lower cutoff. Most phenomena will have some cutoff based on the Fermi level or the gap that is there in the system. But the fact that they are gapless and does not have a low energy cutoff is also a big advantage in quantum computing. I'll come to that next. So the first thing I want to talk about is the terahertz gap. Again, you might all be familiar with this, but let me just indulge me for a second. You can produce high wavelength electromagnetic waves using classical antennas. The wavelength is proportional to the size of the antenna in that case. And when you want to go to very low wavelengths, typically you use quantum phenomena like electronic transitions, right? There's a place between this low wavelength and high wavelength, which kind of lies at the place of the gap of most materials. It happens to lie in the terahertz region of the electromagnetic spectrum. In this region of the electromagnetic spectrum, it's very hard to produce it. It's very hard to detect it too. And this is called the terahertz gap. Classical antennas are too lossy, but there is not enough energy for quantum transitions. This terahertz gap is very important in quantum computation because there are phenomena in quantum computation which work very well on one side of this gap and other things which work very well on the other side. So we want to be able to go from one side of this to the other. Dirac and Weyl semimetals are unique because they don't have a gap. So they might work as very good transducers in order to go from one end of this to the other. How does so yeah, this is ongoing work, and it's I don't have numbers to show you, so I don't want to give you the wrong idea here. But for example, photons are well suited for transmission, and superconducting qubits are better suited for quantum gates. But superconducting qubits operate at microwave, and fiber optics operate at infrared. They are on either side of this terahertz gap. But we can use whatever I just described in order to optically affect the Weyl fermions in order to affect frequencies on both sides of this gap, because these Dirac and Weyl materials don't have a gap in their spectrum. So this puts us in a unique place to do that. We're still doing calculations for this. I don't have any numbers to show you, but most of the transducers which work in this region are incredibly inefficient. So we are hopeful that we will be able to do better than that. The second area where you might be able to use these chiral fermions is in the design of a chiral qubit. So my supervisor and Chang Li here at BNL came up with this proposal for a chiral qubit a couple of years back. Essentially, this is what it is. It is a ring supporting Dirac or Weyl fermions. It's a ring, so it's one-dimensional chiral fermions. Unfortunately, we do not have any systems with one-dimensional chiral fermions yet. But if you have a ring, it's Dirac or Weyl fermions, and you put magnetic flux through the middle of that ring, you can show that the Hamiltonian of that system is exactly the same as the Hamiltonian of a squid-based qubit. So, and the states are just left circulating and right circulating currents or superpositions of those currents. You can superpose those currents, and I just described a way to optically create those currents. You can also entangle those using near field electromagnetic interactions. We don't have an experimental system, like I said, but there is promise, because we know that this Hamiltonian has this analogy. Why would we want to do this? First of all, this chiral phenomena might be observable at room temperature. 3D chiral phenomena has been observed at room temperature, so they might be robust. Second thing is, because they are gapless, they can be operated very fast. Superconducting qubits cannot be operated beyond a certain frequency because of the superconducting gap. But chiral fermions can be operated at terahertz frequency. So even if the coherence time of these qubits is not very high, or as high as that of superconducting qubits, just because you can operate them very fast, the ratio of coherence time to gate time can be very high. Their estimate is that it's about 10 to the power 4. So this is also a direction which is worth exploring. That's it for me. I primarily worked on Weyl fermions. This is just some of my work. Chiral terahertz Weyl fermions and things like that. Now I am trying to learn something about topological quantum computing and qubits, also with the hope of maybe being able to contribute something to this field. With that, I come to the end. I would like to acknowledge my supervisor, Dimitri Kharzev, and my collaborator, Sahel. And this is the main reference for the talk. And I did most of this work while I was a student at Stony Brook University. And yeah, thank you. I would really encourage you to ask questions, and I'm happy to discuss further.
Thank you very much, Evan. So questions, please feel free to unmute yourselves and ask questions. Maybe I can ask a quick question. So the qubit states in this chiral qubit are defined as basically various energy levels, similar to the superconducting qubits.
So the analogy is the following. In superconducting qubit, you have the presence and absence of this particle, essentially, right? In this case, my two energy levels are the superposition of symmetric and antisymmetric superposition of left current and right current.
I see.
So basically, left-handed particles, because of the character of the momentum I just described in this qubit, would only circulate in clockwise direction, and right-handed particles would only circulate in anti-clockwise direction in this case. And their symmetric and antisymmetric superposition are the two states. That's the analogy. Yeah.
Maybe I can just add to it a little bit. So if you look at this effective potential, then you see that if you expand cosine, let's say around 0, you find first a correction which is quadratic in the flux, and then a correction which is quartic in the flux. And so it looks like an anharmonic oscillator.
Right.
That people use for qubits in superconducting devices, because you want this anharmonic structure. So now the reason this beta appears in the case of a chiral qubit, it stems from chirality flipping transitions, because this cosine really comes from the term in the Hamiltonian where a left-handed fermion becomes a right-handed fermion and vice versa. So it's possible to tune presumably this beta by maybe by introducing impurities, magnetic impurities, and so on. But the surprising thing is that even though the underlying physics is very different from superconducting qubit, the final Hamiltonian really has exactly the same form as the conventional superconducting qubit, as Ivan explained so nicely.
So these, so just maybe if I may, so these sort of basically the sort of the lowest energy levels correspond to these various superpositions of.
Yes. So as Ivan said, the ground state and the excited state really correspond to symmetric and anti-symmetric superpositions of left and right movers.
Makes sense. Okay.
Mm-hmm.
So for physical realizations of the 1 + 1 problem, have you considered like nanowires or very small radius nanotubes, metallic nanotubes, which could have propagation properties like massless fermions in 1 + 1 dimensions?
Have we thought about it? Yes, but we wanted to. So one thing we want to do is to arrive at this Hamiltonian from some first principle calculations. We have not completed that, but yes, we have thought about using them, but that's the stage we are at. We don't have a first principle calculation to get to this Hamiltonian from the Hamiltonian of a nanowire system yet. Hopefully, we will have it soon.
Hi, this is Neeraj. Can I ask a question? A simple question.
Sorry, your sound sounds very robotic. I can't. Maybe you can type it in the chat. I can just. We have, yeah. There seem to be, or if somebody else can hear him, then.
you don't say anything, we can't.
Can you hear me now?
Yes, clear.
Yeah. So you predicted the magnitude of the current for the Weyl and Dirac material, right? Zirconium
Yes,
pentatelluride, platinum arsenide. But
yes.
somewhere in the talk, I think you said that the current magnitude does not depend on the material properties. So I'm curious, what features of the band structure or the material property did you put for those materials?
Okay, so that was not, I am sorry, I misled you a little bit in that it was not intentional. The current does have one parameter which is material dependent. I'm sorry, I unshared the screen. Let me just share it again. So current, there is one term in that Hamiltonian which does depend on the material property, and that term is actually the I'll show you. Yeah, so if you look at the expression for the current, the only place where the material enters in is this sigma ZZ2 term. So there is this sigma ZZ2 term. This is a material dependent term. Everything else is independent of the material. And this sigma ZZ2 term enters the calculation because there are chirality flipping transitions in these things. Essentially, it depends on the tau v, right? The chirality flipping, the chirality flipping length scale or time scale. That's the material dependent parameter that affects this. There's also something else. The number of cones also affect the magnitude of the current. Tantalum arsenide and zirconium pentatelluride has different number of cones. Plus, the resistance of the material is also going to affect how much current you get out of it. The current itself doesn't depend on the resistance, but the way you measure this current is by putting an external probe, right? So this external probe will have some resistance, and these are semimetals. So there will be an internal circulation of current since they are semimetals. So we have accounted for all those things in this estimate that we have given. The internal circulation of the current, that depends on the resistance of the material. The number of cones has been taken into account, and also the chirality flipping time scale has been taken into account. Sorry, I made it look like it doesn't depend on anything.
Yeah, so I have one more follow-up question then. So you mentioned the dependence with the number of the cones, right? And for zirconium pentatelluride, since this is a Dirac material, once you put magnetic field, I think it becomes wide, so the number of cone doubles, right? So did you include that, or did you do the calculation for?
So here, what essentially happens is, that's a good question. But here it depends on the number of pairs of cones in some sense. So in case of a Dirac material, if you count one Dirac cone as one cone, it's actually two Weyl cones sitting on top of each other, right? So it only depends on the number of cones in that sense. The tilt of the cone and things like that will actually enter into this. I haven't shown that in the expression. We know how to do the calculation, but even details like the tilt of the cone and everything will enter into it. We have this convenient way of putting all that into this sigma zz term. So we have kind of put all that into sigma zz. So let me put it this way. If you want to calculate it from band structure, the easy way to do it would be to calculate sigma zz2, which is the coefficient of magnetoresistance, the quadratic magnetoresistance coefficient. If you calculate that from the band structure, then you can just plug it into this expression.
Okay, thank you.
May I ask a question too on this slide? So you mentioned that the current doesn't depend on the conductivity, which is sort of strange.
Oh,
I
no,
would
no, no,
imagine that
sorry.
the penetration depth decreases as you increase the conductivity, and so you can generate an infinite current in an infinitely thin surface layer of a metal, probably. So the total current would still depend on the conductivity.
Two things. First of all, when I say total current, if I am referring to the total current that is generated, it does not depend on the conductivity. I will come to that in a second. But the current you take out with a probe will depend on the resistance of the sample just because of the measurement technique. But I suppose that's not what you're referring to.
No,
right?
what
You're
I'm
talking
saying
about
is
the
that
current
just
that's
the
generated.
illuminated area of the material will, the skin depth
Yes.
will depend on the conductivity.
Yes.
And so the amount of material in which you generate your current density will decrease with increasing conductivity.
Yes. So the reason why conductivity doesn't get into this expression is because of the following. We assume that the entirety of the light that is falling on the crystal is getting absorbed by the crystal. So if the light is going to get absorbed in 100 nanometers, this current will be distributed across that 100 nanometers depth. If the light is getting absorbed in 5 nanometers, this current will get distributed in that 5 nanometers depth.
Is it not a current density in your formula?
So what this
is it not a current density?
Yes,
current density is transformed into a current by multiplying by a cross section. And so what I'm saying is the thinner is the sheet in which you generate your current density, the smaller is your current.
So it will depend on the amount of area that, couple of things. First of all, my Dirac material has to be thick enough that the entirety of the light is being absorbed by it. Otherwise, this formula is not valid. But the skin depth of these materials is very small. So unless you are talking about nanometer thin sheets, you don't have to worry about the light getting through it. It gets absorbed in, I think,
no,
like
I'm worried
tens
about
of nanometers.
light not getting through it. If you have a millimeter thick sample and light will be absorbed in the first 100 nanometers, then it's only in the first 100 nanometers that you will generate your current density.
It could be a two-dimensional surface current density, right?
Yes. So, actually, I should have said that directly. What the current is actually this number has to be this is a two-dimensional current density that's integrated over the depth over which it's generated. And this doesn't depend on the spot area, it only depends on the spot width. So what you get an expression which doesn't depend on the conductivity if you integrate it over the depth of the sample. So this is linear current density on the surface. That's what it is.
So
I'm not sure if I explained that correctly, but yeah.
The other remark I had is concerning the absence of the gap. In these materials, if you have a really Weyl or Dirac material and the Fermi level is close to the Dirac point, the conductivity is poor, and so, like in graphene, it's well known that there is a large variation of the chemical potential. Of course, your whole consideration is based on on assuming that you have either electrons or holes. So inhomogeneity of chemical potential, which is present, for example, in graphene on the substrate, will violate the entire consideration if your filling is lower than some certain filling, such that all your particles, that all your sample is filled with electrons, no holes.
So one thing is, again, I do not know about graphene that much, but this phenomena will only happen in three-dimensional when you have three-dimensional.
What I'm saying
Dirac
is that
Weyl
instead of a
fermions.
gap, you have a cutoff, which is introduced by the variation of a chemical potential in a poorly conducting material. I mean, it's just a material issue that you have to be aware of.
you are right. We have assumed that Dirac and Weyl materials have well-behaved chemical potential. I am not, I haven't looked into that, and that might be a practical consideration that we have to take into account. But in these negative magnetoresistance experiments and things like that, from what we have seen, we assumed that these things had relatively well-behaved chemical potential. But thank you for pointing that out. We will definitely keep that in mind.
It's not really very close to the Dirac point, so that's not.
All right.
I mean, getting into that regime.
I need to wait.
Common.
I need to say something now. I mean, I think it's appropriate to ask the speaker questions. I feel like it may be verging on inappropriate to harass the speaker with repeated instances of the same question. So I would like to ask that we try to tone it down a little bit.
Well, I apologize. I didn't mean to harass. Actually, I thought it was no intention remark. I apologize.
It's okay. I mean, I think passionate discussions are actually pretty good, but we should also sort of try to curb it in the interest of time. So maybe.
So can I ask a question here, Evan?
Sure, please.
Sure.
Yeah. Okay. Well, let's go back to the first question. Igor mentioned about that one. It's not a really issue over there. It depends on frequency, as you can say. If you work on the terahertz frequencies, you can get the millimeter wavelengths over there that can penetrate a couple of thousand nanometers. So that shouldn't be a problem. The other thing is that your omega over there actually go to lower frequencies. The current will go bigger. The other thing is the conductivity part of the light is that most of the semimetals, and they are not at the Dirac point. So you have a substantial amount of the carriers. So it gave you the conductivity. So that's, I think it's measurable. We're trying to measure that. The real question I have for you is that you say it's not material dependent on them. So at this current, the circular polarized light and magnetic fields, any relation to the direction of the cone? If you have a cones aligned in plane, is that going to work or not?
This particular effect is insensitive to the relative orientation of magnetic field to the cones.
I see.
But because of the because this comes straight from the conservation equation, it shouldn't depend on it. But there are other effects which usually happen because of those kinds of things. So the current might be, so as to speak, polluted by other currents as well, if you have tilted cones and things like that. The ideal setup to see just this would be a Dirac material, because if you have a Dirac material, you don't have any other currents. You will only see this current, so it will be clean. But you are the expert in the material, so practical considerations you definitely know better than me. Well, and thank you for those comments.
Yeah, you're talking about other excitation could come up with the current, but that's very easy to do. Is that you change your polarization over there, and this current direction is dependent on the polarizations, right? And if you find precisely. That changes with polarization, then you know it's your current. Otherwise, it's just a thermal current being used. So that's discernible.
Yes.
Okay, that's all.
So we
talk then.
We are really thank you very much for the comments. We want to work closely with experimentalists, even though especially with the lockdown that has not been possible. And we learn a lot, especially from these kinds of comments from you, because we tend to consider it to be an ideal system. And in reality, that's not the case. So every time you give feedback like this, we learn that, okay, there is one thing more to take into account. So thank you so much for those comments.
You're welcome.
I'd like to ask a question, if I may, about the kind of qubits that correspond to your ground space, or your low energy space qubits. I mean, one of the you post a lot of advantages for working with a gapless theory, but I guess there are also some natural disadvantages to working with a gapless theory. So I guess my question is like, how I guess how fine is the logical Hilbert space that you're using of your low energy excitation energy levels that correspond to your qubit states? Because their energy difference is very small, then it can be very difficult to check if you have either the state you want or another state that happens to have very similar energy.
So we don't have any first principle calculations based on any crystal structure or materials yet. So as far as I know, I don't. Would Professor Khazev be able to make any comments on this? I don't know. But as far as I know, we don't have any handle on those things yet. So you're absolutely right. This there are a lot of disadvantages to this. Like I don't know if we can answer that question before we get to this Hamiltonian with some first principle calculations. So I don't know. That's my answer, but maybe Professor Khazev has sent some comments.
Yeah, I think he left already. So if
okay,
he's not going to get,
yeah.
But like,
sorry about that. Yeah.
I'd like to just try to say why this is an interesting question to me. It's one thing, I guess, to design a physical system and to say that, like, in principle, these are things that can operate as quantum charge carriers, and so I can distinguish these qubits from each other. But in practice and operationally, one needs to have a way of actually distinguishing the various qubits from each other in order for it to be functionally useful as either a quantum sensor or like a potential way of implementing a quantum information theoretic process. And I guess that's the thing really missing here, because it seems that like unless you have a good answer to this question, you kind of run the risk of doing something and setting up something maybe even kind of expensive experimentally, but then at the end of the day finding out that it's actually not useful or usable in a quantum sense because of the kind of the gapless structure. So I think that I would strongly suggest figuring out the answer to this question, or at least the in-principle answer to this question, so that there's a stronger motivation for this as something that's relatable to QIS.
Yeah, no, I absolutely see your point. Yes, and this is more fundamental than many of the concerns that we were thinking about so far. So yes, I do see your point. We don't have any real numbers associated with this proposal at the moment, actually, because we haven't been able to get to this Hamiltonian from some first principle calculations based on some tight binding model or something like that. That's what we were thinking about as the first step. But yes, I do see your point, and that's not something we have been keeping in mind, that the symmetric and antisymmetric state might look different on paper, but that doesn't mean you can distinguish them easily in a real system. Did I understand that correctly? Is that what you're essentially saying?
Yeah.
Yeah. Okay.
So can I add something here, because I'm an experimentalist here. So I'm Charlie from Donneberg and Brookhaven. So I think you have a very good question over there. Actually, from the experiment side, we were implementing experimentally some of the test bed to test this chirocubic concept. The two-level systems is left-handed, right-handed ones, and superposition is basically the current, circulating current there. So, and we have two papers out. One is PRX over there. We will be able to use circular polarized light to tune the systems and give emissions. These terahertz emissions carry the signature of the chirality because it also have a chiral symmetry of that. And that one will be able to communicate with the next ones. We actually have a patent of this chirocubic, which awarded this year But there are many more details of that one. So one thing is that how you're going to make the two qubit communicate there. And one of the ways we were saying, instead of using microwave cavities, you guys use for superconductor qubit, we were talking about terahertz antennas, transducers to make them communicate. There are a number of schemes work out. It's working up now, so we don't have anything concrete yet. But I'm happy to talk with you because I'm an experimentalist, learned more of what real systems, device side, how they work. So any other times and we can get together and discuss how we do that. We have some preliminary studies, and it seems to be promising. We at least get the emission out of it when you're shining a circular polarized light, and that carry the signatures, and hopefully going to be a medians for do the transductions.
I mean, I have actually not done any successful work on this. My main interest in this was to try to come to this Hamiltonian using some realistic model rather than just having a Hamiltonian out of nowhere. That's the only side of this that I have looked into. But yes, we have experts here at BNL itself who are working on this. Again, thank you for your comment.
I think that, Jang, I think to answer your question or your statement, yeah, I'd be happy to talk. There are, I guess, two main issues that I'm not sure how to address that come from the gapless criteria. The first one is one of the ones that you already mentioned, which is how do I ensure that qubit 1 talks to qubit 2 and that this specific energy level qubit 1 and this specific energy level of qubit 2 talk to each other, and there isn't some small fluctuation where qubit 1 star is the thing that's actually talking to qubit 2. How do I ensure this crosstalk in systems like that? I think that is very hard in a gapless system. It may be more possible if you have a gapless system that has a particularly sparse low-lying density of states. Even then, you would need to engineer your system to have that property. The second thing that I would be concerned about is readout. And like I would, even granting that you can run your entire thing to implement whatever unitary circuit you're trying to implement, I would have concerns about your readout fidelity. That like if I'm really trying to determine if it's qubit 1 or qubit 1 star and they're in the same, their energies are very close to each other, that readout seems to me like it could be very difficult. Maybe you already have an answer to this, but like I'm not really sure how that would work.
Yeah, like Changli also mentioned, there are some there's some very preliminary. There is some work which deals with terahertz emission from chiral materials, which and the near field interaction of those things, as he mentioned, is what is the current idea to get these things to talk to each other. But the concern you mentioned is not something that we have been able to theoretically address. Maybe experimentalists will actually try it before we even are able to do it. They are moving much faster than us in this. But yeah, concerns, both the concerns you brought up still stand. We haven't been able to address them yet, even though we have some way of talking to each other and some way of reading it out. Actually, readout is mostly through this chiral magnetic photocurrent like effect. We have a way to read out and a way to talk, but we haven't been able to address things like crosstalk or how likely are we to confuse the readout and things like that. Yeah, those concerns stand. And this is very much work in progress. That's why I said in the beginning, some things might even border on speculative territory in the application part of this talk.
Okay, thanks. Also, Layla left and asked me to close the meeting. So if anyone is staying around out of a sense of obligation, they should feel free to leave if they want to.
Yes.
I think the meeting will remain open for another 5 minutes or something. So if other people have questions, also feel free.
All right, I'm done. Have a good talk.
Okay, thank you so much. And also partly why I talked about even the speculative stuff is because we have people here at BNL and Stony Brook, and what we are actually trying to do is to try to learn more about this and explore these ideas. I don't have a background in qubit design or anything related to that. So I am coming from a different side and trying to learn more about these things.
Great.
Okay,
Are there any other questions? Okay, it doesn't sound like there are any other questions. So I guess with that, let's thank you, Evan, for giving the talk, and we'll see you guys next time.
Thank you so much. Bye-bye.